Hello and welcome to the last portion of this homework. I will be doing part D of this homework number 2, in which we'll be implementing an iterative Rashford-Rice calculation to calculate the VLE of an isopropanol and water system. We are going to explain how good guesses for the vapor fraction and liquid composition can be obtained from the calculations that we already did, in which we already labeled. And then we're going to check our results for feed composition of 25% mole isopropanol at 1 bar, 360 Kelvin, and compare that to the diagrams we got in part C. So as you can see, I already have this pulled up here, and we can continue with our good guesses. So the first step in completing this, we're going to define our due temperature using NRTL, and that's going to be of functions y composition and pressure. And then we need to say that T of 0 and X of 0 are going to be equal to our due temperature of functions composition y and pressure. And then V of 0 is going to be np dot r underscore brackets T of 0 X of 0. So now that we have all of these defined, we're able to now find our roots, and we're going to have to define fruit first. And we'll be finding the roots of V, and we need to say T is equal to V of 0, X is going to be equal to V of 1, so this is saying the first value is going to be equal to our T and the second value is going to be equal to our X. Not second, but sorry, 0 is going to be equal to T, and then from 1 everything on is going to be equal to our X value. And then obviously we have to return our values, and we want to return our np dot r underscore x times r dot nrtl underscore gamma of x and t. This has to be multiplied by r dot pvap underscore t, and then that will be p minus y. And then we also need to return our sum of x, and that's going to be minus 1. Is that all? Yeah, that's all in brackets. And then we still have work to do. We have to do res equals sp dot optimize, which we have used multiple times before. Root. We want to find the root of v0 dot x, and then again we need to return so we can answer these problems. Sorry, they're doing construction outside of my house if you can hear that. We need to return our resolution values. Let's make sure this runs correctly. Oh, I need a colon there for all. Okay, we are now good to continue. So now the next portion, we're actually going to be introducing the Rashford-Rice calculation. And to do this, we're going to be using those equations that we found actually in part A of this when we derived the Rashford-Rice. To do this, we have to define the flash calculation of our pressure and temperature, again, NRTL. And now the variables we will be using: Z, which we had in our equation, our pressure, our temperature, and then our niter variable that we have been using today. And then total will be equal to 1 e to the minus 6. Alright, so now we can begin. We want dp and x due, and these are all going to be equal to due p underscore nrtl of functions composition z and temperature. And then we want our bubble pressure to be bubble underscore y to be equal to bubble p nrtl, again a function z and temperature. And now we have to create our if loop as we have done before. We actually I was going to copy paste it, but it does not matter. So if our pressure is greater than our bubble pressure, we want to return a value of all liquid Get out of that. Now, if our pressure is less than the due pressure, then we want to return a value saying all gas. So now we're able to get out of that if loop, start a new thing, and we want phi, that variable with looks like a 0 with a slash through it that we used in our derivation earlier. We want P minus boiling pressure divided by due pressure minus our boiling pressure. Now we want X equal to phi times X due minus Z plus Z. Seems a little counteractive, but since it's in the parentheses, it is not. And then we have to make another for loop for I in range of the niter function that we typed out above. We need to say K is going to be equal to R dot NRTL underscore gamma of function of composition X and T, and this will be multiplied by R dot PVAP of temperature and pressure. Now the next thing, again, we're going to have to define our roots inside the for loop. We want to define the roots of our phi value, and we want to return JNP dot sum of Z times our K minus 1 value divided by 1 plus our phi value times K minus 1, and we want to say that our fruit prime is equal to Jax dot grad of our root still a lot more to go here, so we need to do phi is equal to sp dot optimize dot root underscore scalar, and in this we need our fruit. We need to say x0 equals phi. We need to say method is going to be equal to prime, and then f prime is going to be equal to fruit underscore prime, and at the end of this we need to say dot root. And now our x new value is going to be Z divided by 1 plus phi times our K value minus 1. And then create an if loop if np dot linalg dot x minus x new is less than total. We need to say x equals x new, create a break. And say x equals x. Now I need to do this for our y variable. So completely get out of here. We need to say y equals k times x, which we again got all the way from part A. So we need to return our variables now of phi x and y. So now we will be able to run this and see if we have any errors. So I had to use the help of some Gemini here. I did realize that you can see all edits I had to make. I had a couple K's that were meant to be uppercase and they were lowercase, and then I also spelled return wrong a couple times. So the last thing that we're going to do here is add a flash dot pressure temperature. Oh, get that out of there. Flash PT NRTL. And so this value, or these array, is going to let us see our compositions of vapor and liquid. And given to us were these specifications that we need for this, which are 0.25, 0.75, and then 1 e to the fifth, and 360. And so now let's run all of this. Let's see if we get our given the values we are looking for. So we do have an error. Told TO is not defined. Look into this and I'll be right back. So we were able to fix this. I had to rearrange some of the order in which I typed stuff above. It got a little bit funky since I was typing in the same separations homework as part 2C. So essentially, after we fixed all of the code, we were able to go in here and use the Ratchford Rice iteration that it asked for here. And we plugged in our 25% here, mole composition. We also wanted our at 1 bar and 360 Kelvin. And you can see that's there. And so you get your liquid and gas composition. Here's the liquid, it's isopropanol and water. Here's the gas with isopropanol and alcohol. And so you can now see that using that Ratchford Rice that we started with at the beginning A, we wrapped it all the way up here in part D into getting these nice arrays to find our liquid and vapor fractions.